Okay, good morning. Welcome back. Um, as I said in the announcement, which I hope you got by email, from now on, we're going to do attendance the way we did it last time by just me asking a question about what we did in class and you answering it at the end of class, and any relevant answer counts as having attended. I like that a lot because it gave me a sense of what you took away from the lecture, what you thought was important. So I think it has two uses. One is it gives me information, and two, it lets you reflect on what happened. Today we're going to continue talking about internal energy. So up to now we've been talking about the randomized kind of thermal energy that's associated with these microscopic motions of atoms and inside an object. But not all internal, and not everything we want to call internal energy is this random thermal energy. Okay, some of it is actually more organized. And so we're going to talk about larger motions, bigger contributions to internal energy. And we're going to learn to calculate, in particular, rotational energy, which is something that came up last time and something we need to be able to calculate. So that's the agenda for today. So let's start by thinking about something like a frisbee. So consider a frisbee. A frisbee has, you throw a frisbee. It has momentum. It has energy. You can calculate the energy of a frisbee, presumably the kinetic energy of a frisbee, by just using the equation for kinetic energy. So we would calculate, if we had a frisbee, it had a mass of 140 grams, and it was traveling at a speed of 15 meters per second. We could calculate its kinetic energy. Its kinetic energy is just a half times mass times speed squared, so it would be a half times 0.14 kilograms times 15 meters per second squared, which would give us something on the order of 16 joules. But that doesn't capture the fact that the frisbee is also rotating. All this tells us about is the motion of what we can call the center of mass, the center of the frisbee, the center of mass. And so what we want to do is we want to break down energy into energy associated with motion of the center of mass, and this is called, in physicsy terms, translation. Okay, this doesn't have anything at all to do with translating from English to Russian. What it has to do, the technical term translation in sciences means moving an object or the center of an object from one location to another. So that's called translation or translational energy. And energy associated with motion relative to the center of mass. And so this is what we mean by this is internal energy that's not randomized thermal energy. So this is more organized. So not randomized thermal energy. And so what we're going to end up with is some expression that's sort of like this. It's going to say the total energy of something is its rest energy plus the kinetic energy associated with motion of the center of mass. We're going to call this the translational kinetic energy plus energy associated with motion relative to the center of mass. So we're going to call this E rel and this E translational. And this is going to have various components. It's going to involve, it would involve vibrations. So for vibrations, we have the kinetic energy of vibration and the spring potential energy for vibrations. And then it's going to have this kinetic energy associated with rotations. So that's the goal of what we're going to be doing today. So here's an example before we get down to defining things. So here's an example and of what we're talking about here. And I'll show you in a VPython program. So here we have two objects that can move, okay? A blue one on top and a red one on the bottom. They're dumbbells, basically. They've got masses on the ends, and then they've got a low mass bar connecting them. And if we let them move, it makes sense to ask which one has more of something. So we can see that in some sense they're moving at with the same velocity, because the objects move across the screen at the same rate, and yet there definitely is something different going on. So let's ask the following question. So let's think about the momentum of the objects, okay? So consider the momentum of these moving objects. And we have a question here. So for which object is the momentum greater? So the magnitude of the momentum. And indeed, the answer is what most of you said. They have the same momentum. Because think about the definition of momentum, gamma mv, or approximately mv if they're moving slowly compared to the speed of light, which they are. So they have the same masses, they're moving with the same velocities, they have the same momentum. Now, if you said the red one, the bottom one, had more momentum, you're probably responding to an impulse that they've got something more. But momentum isn't what they've got. So let's try a different question. Okay, the question is going to be, which object has greater kinetic energy? So now the question is not momentum, but kinetic energy. Which one has greater kinetic energy? So what you said was that the majority, but not a big majority, said that the red one, the one on the bottom, has greater kinetic energy, and the one on the top has less I'm sorry, you said they had this. You said the one on the bottom has greater kinetic energy. Some of you said that they have the same kinetic energy. And we can see that this is, so the answer is the one on the bottom has the greater kinetic energy is correct. Okay, and they don't have the same kinetic energy. And we can see this by actually looking at the velocities of the balls themselves. So we can see that in any instant here, each red ball has a velocity that's greater than each blue ball does. And so if we add up the kinetic energy of the two red balls, it's going to add up to more than the kinetic energy of the two blue balls. This is sort of cool. I don't know how informative it is, but you can actually see the path traced out by each object, and you can see that each red sphere is actually moving farther in the same time than the blue sphere does, so therefore it actually has to have a higher speed. So we need to be able to capture the fact that there's another piece to this kinetic energy. It's not just how the center of this thing moves, but it's actually related to this motion relative to the center of the object. So that's our goal for today. So to start doing this, we need to be able to quantify this idea of what's center of mass. Now you probably have an intuitive idea of what the center of mass of an object means. It's the place that you could balance it. So here's a ruler, and there's a place in the middle where I can balance it on one finger, which sort of says this is kind of the center of the ruler. The center of mass is a weighted average, whereas if I try to balance it over here, it doesn't work. And so what we want to be able to do is to be quantitative about this idea of center of mass, and so we can actually use it in calculations, because the idea is we're going to be talking about the motion of the center of mass of the object and then motion relative to the center of mass, which is what this rotation thing was. So the center of mass is kind of a weighted average location. And it's defined, it has a vector position, okay? So relative to some origin, the position of the center of mass is the weight, the sum of the positions of all the little pieces of the object. It could be all the atoms, or it could be the two spheres in our dumbbell thing, divided by the total mass. And so what we have is, it's the mass of object 1 times the position of object 1 plus the mass of object 2 times the position of object 2 divided by the total mass m1 plus m2 plus, okay, so however many objects we're considering our system as being divided into. Okay, so that's the definition of center of mass, and let's see how it works. So suppose we had a dumbbell, one of our dumbbells from the program we were just looking at, and let's say each of these spheres had a mass of 2 kilograms, and the length here is 1 meter, and let's say that we place it so that the center of the bottom sphere here is at y equals 0. So this sphere is clearly at y equals 1 meter. And so presumably the center of mass here, if we're, for the moment, we're neglecting the mass of the rod. These are massive balls, and so the rod has a low mass compared to the balls. So we should expect the center of mass to come out somewhere near the center of this thing, presumably. And we can calculate it. So this position of the center of mass is equal to 2 kilograms times 0, 1, 0, that's the top sphere, plus 2 kilograms times 0, 0, 0, that's the bottom sphere, divided by 2 kilograms plus 2 kilograms. And so what we get is, we get 2 over 4 times 0, 1, 0, which is equal to 0.50 meters. These are meters. Which is basically where we thought it ought to be, right? Halfway up the rod. Not everything is symmetric. So suppose we had an object that was a composite object, and it was made of 2 spheres, but this one had a mass of 10 kilograms, and this one has a mass of 2 kilograms. And this one's at location, this is 1 meter, and this is at 3 meters on the x-axis. Now, we wouldn't expect the center of mass to be in the middle of these two objects because, so you can imagine they're connected by a low mass but very strong carbon fiber or something, because the object on the right is so much more massive. So in this case, the center of mass would be at 2 kilograms times the position of the first one, which is 100 meters, plus 10 kilograms times the position of the second, which is 300 meters, divided by 12 kilograms. And this gives us 3200 kilogram meters divided by 12 kilograms, and that's going to be something like 2.6700 meters. And that's basically a lot. That's pretty close to this big mass. Our center of mass actually comes out here. So the question is, does the position of the object change the position of its center of mass? And what I think I would really say is the position of the composite pieces of the object change the center of mass of the whole system. So if these two spheres are the system, then their relative positions are gonna change. If you change their relative positions, you will change the center of mass. Even in the case of our symmetric dumbbell up here, the one along the y-axis, if you made it longer, so if you had, if this was 4 meters, and it was 4 meters long, then the center of mass wouldn't be at 0.50 anymore. It would be in the middle of these two things. So it would be at 0.50 0.20 meters. So you take into account the position and the mass of the objects. The interesting thing about center of mass is that there doesn't have to be anything there. So the center of mass of a system made of a collection of objects could be at a location where there actually isn't any mass. So suppose we had some sort of set of masses on spokes, and everything had the same mass and the same length of the spokes. I think it's pretty obvious that the center of mass would be here at the center of this object. But suppose we had instead a hoop. So we had a bunch of objects together, glued together, making up a hoop, and they're all the same mass. And the center of mass is actually going to be in here, even though there are no atoms there. Okay, so this is a mathematical weighted average of the, a donut. Well, a donut does have a center of mass. It's in the center of the donut. Now, so any questions about the definition of center of mass or how you calculate it? Okay. So how is this useful in talking about motion and energy? Yeah, absolutely. That's what we just said. There's always any object, any system, collection of objects has a center of mass, whether or not there's an atom there. So how can we relate this to motion? I don't understand, Alexander, what you mean, do we correct for the math? Yes, Seth, that's exactly right. We're going from modeling systems as point particles to actually talking about extended systems and acknowledging that when we model a system as a point particle, so this is a really good point, thank you. This is a really good point. When we model a system as a point particle, what we're doing is we're imagining that all of its mass is squashed down, is located right at the center of mass. So Superman comes along and squashes it down to the center of mass. And that tells us a fair amount. I mean, we still get the right momentum, for example. But what it doesn't tell us is about stuff like this rotation, which we really want to capture. Now we can get a center of mass of objects that are not composed of discrete objects, and I wonder if this is what Alexander was asking. So suppose we just have a hoop here that's a continuous hoop. So the way we'd calculate the center of mass of this is by dividing it into a whole bunch of little pieces and treating it as if each piece was a discrete piece of matter and adding up their positions relative to some origin here. So we'd have the position of this object and the position of that object and the position of that object. And of course, if you make these pieces really, really small, what you end up with is an integral. So, well, I'm not sure. Is it more of a relationship than a property? I'd say it was a property of an object, of a particular object, which captures in some way, it's related to the distribution of mass within the object. So we have this definition: the center of mass is equal to m1r1 plus m2r2 plus whatever over m1 plus m2 plus, and we can of course, this is just the total mass of the system, so we can write it as the total mass of the system. And we could, of course, multiply through by the total mass, so we get total mass times RCM is M1 R1 plus M2 R2 plus ... And we know that so Seth, do the masses have to be equal in magnitude? No, of course, and they don't, and we did that example. So here's the example we did where the masses weren't equal in magnitude. Our system was a 2 kilogram mass and a 10 kilogram, right? No, it's not stupid. It's just putting it all together, right? So, well, let's see about center of mass and motion here, and we'll come back to this, okay? So we know that that dr dt is just a velocity, right? So if we differentiate both of these sides with respect to time, what we get is that the total mass times the velocity of the center of mass is equal to m1 v1 plus m2 v2 plus, and this of course is just the momentum of particle 1, and this is the momentum of particle 2. So it looks like this is the total momentum of the system is going to be equal to which is equal to P1 V1 plus, P1, sorry, plus P2 plus. So the total momentum of a system is equal to the total mass of the object times the velocity of its center of mass. Okay. Well, we know that kinetic energy is its speed small compared to the speed of light. Kinetic energy is a half mv squared, and it's also equal to the square of the magnitude of the momentum over 2m. We can also write here that the translational kinetic energy, kinetic energy associated with motion of the center of mass, is equal to a half times the total mass times the magnitude of the center of mass velocity squared. And this is going to be equal to the magnitude of the total momentum of the system divided by m total. Now remember translation. There was this word that meant, this word that meant associated with motion of the center of mass. Okay. So what we can calculate with this a half mv squared, which we did at the beginning of class for the Frisbee, this is translational kinetic energy. It's associated with motion of the center of mass. But it doesn't, as we see with the Frisbee or with that rotating dumbbell that we saw in that first animation, that's not the whole story, right? So we need to get the total kinetic energy. we need the translational kinetic energy plus this kinetic energy relative to the center of mass, so vibration, rotation. The reason the center of mass is important for things like aircraft and rockets has to do with torques and balance. So it's the same idea as balancing the ruler, right? If we don't have what we have here is, and we're edging up into a topic called angular momentum, where we'll see how this works. But the idea is that the Earth is pulling down on this end of the ruler just as much as it's pulling down on that end of the ruler, and so it's equally distributed. But if you get an unequal pull, then things tend to rotate, and that's awkward. Well, you do know what kinetic energy is. We're actually just we're enriching our definition by deciding that we no longer are going to want to be restricted to modeling atoms as point particles. Yeah, balancing cargo loading on airplanes really is important. Otherwise, when you're flying, you're trying to counteract this big torque that's going on. A torque is a twist, right? A difference in gravitational pulls. Okay. So let's take a minute and think about the kinds of energy in different moving systems. So let's go back to the Python here. Let's consider, okay, this is a simple case. So let's consider we have a system that's now two masses connected by a spring. And the black arrow is a force, so there's a force applied here. And this magenta end, the left end of this mass is held fixed, but the right end is free to move. So let's see what happens here. When we run it, the right end moves, but the left end doesn't. So what is the velocity of the center of mass here in this situation? Is the velocity of the center, is the center of mass moving? Is the velocity of the center of mass zero or non-zero? Okay, so yeah, the center of mass velocity is actually non-zero, even though one of the pieces isn't moving. We can, whoops. So let's actually show the center of mass velocity. And we can see that because as the thing stretches, the position of the center of mass changes, that the center of mass velocity is actually non-zero. Yeah, it's not, the center of mass isn't moving as fast as the red mass moved, is it? But it's moving faster than the magenta mass moved, which was not at all. Okay, let's think about this situation. So here's our masses in spring, and now it's just vibrating. So what's the deal with the center of mass velocity here? Center of mass velocity zero or non-zero? Yeah, center of mass isn't moving, right? It's just staying there. Is the kinetic energy of this object zero? Nope, kinetic energy isn't zero because these atoms are moving relative to the center of mass. Okay, so that's the, these are the velocities of the atoms relative to the center of mass, and you can see that they're actually So the kinetic energy associated with this vibration is on average non-zero, and the sum of K plus U is certainly non-zero. Okay. Okay, let's think about this case. So center of mass is definitely moving, right? So that's the center of mass velocity. But in fact, these atoms are also moving relative to the center of mass. So that we have two kinds of kinetic energy here. We have this translational kinetic energy associated with the motion of the center of mass, and we have this rotational kinetic energy associated with the fact that the thing is spinning and the atoms are moving, the atoms, the balls, the whatever they are, spheres or. Okay, and of course we can have all three, where we've got the center of mass moving, and we have rotation around the center of mass, and we also have vibration relative to the center of mass. So the relative velocities of the atoms are. Okay, can center of mass be a vector? Center of mass is a vector. It's defined as a vector, right? So it's defined as a vector, a position vector relative to some origin that we have to specify. So depending on, so if we put the origin, say, just to the left of this magenta ball, for example. I don't think I can draw on this. No. We put the origin just to the left of the magenta ball here, where my cursor is right now. Then you can see that the center of mass is moving away from that origin, and so it has a velocity in the plus x direction relative to that origin. So center of mass is a vector. It's defined relative to some origin, and the velocity of the center of mass is also a vector. So you've been asking good questions. What other questions do you have before we go on? So what we need to do, we know how to calculate translational kinetic energy. We need to be able to calculate rotational kinetic energy. So let's think about a solid disk that's like a frisbee, for example, that's rotating. So I'm gonna, whoops, see if I can try to draw something that looks sort of like a solid disk. Great art here. So let's imagine a solid disk that's rotating around a central axis. Okay. Now let's think about two atoms. Let's think about one atom that's near the edge and one atom that's near the center. In one rotation, this atom has to go around that distance. Whereas this atom has to go much further. It has to go all the way around there. So that the velocities of these atoms are actually different. So this atom has to be going a lot faster than this atom to make it around. So that makes life difficult because we don't want to have to figure out the velocity of each atom in this thing and add it up. But what actually is the same for these two atoms? So two atoms. Yeah. Yep. Dylan, that's right. Angular velocity or angular speed is the same. So, but omega, angular speed is the same. Remember that this angular speed is defined as it has units of radians per second. And each of these things go around 2 pi radians in a time t, which is the period, the time it takes it to go around one revolution. Now, how is this related to speed? Well, the speed of an atom, so speed of an atom, so let's see, atom 1, so we'll call this atom 1, and this is atom 2. So atom 1, V1 is equal to the distance it travels, 2 pi r1 divided by the period of rotation. And the speed of atom 2 is equal to 2 pi r2 over the period where r2 is, so that's r2 and that's r1. So in each case, in general, we can generalize and we can say that the speed is equal to 2 pi over t times the radius of that particular thing's motion, but this is 2 pi over t is the period. So there's a relationship between speed and angular speed. So that tells us that v is equal to omega, the angular speed, times r. And here this r is defined, so it's important that r is the distance, is this distance from the center to the atom perpendicular to the axis of rotation. Okay, so r is r perpendicular to axis of rotation. So we can calculate translational kinetic energy now. Okay, rotation is going to be, it would just be a half m1 v1 squared plus a half m2 v2 squared plus all that stuff. And we can now rewrite this as a half times m1 times omega r1 squared plus a half times m2 times omega r2 squared. And if we factor out the omega, we get a half times m1 r1 squared plus half m2 r2 squared times omega squared. Okay, so if we know the angular speed, the number of radians per second that it's going around, we can calculate the rotational kinetic energy And this quantity here has a name. This is called the moment of inertia. This is a very old-fashioned name of an object, and it has a symbol I. So I is defined as a half m1 times r1, and again, this is the perpendicular distance squared plus m2. Oh, sorry, that's the half should come out. So it's this m1 r1. So this is okay, right? So we have K rotation is a half I omega squared. So let's get this half outside here. Now, there is a distinction here between speed and angular velocity. And for right now, we're going to talk about angular speed, which is radians per second, because velocity is a vector, and angular velocity is a vector too. So if we want to talk about angular velocity, we can write it as a vector. And so it's equal to the angular speed, and it has to be times some vector. Well, what vector do you pick when something's rotating? So by convention, what we do is you take your right hand and curl it around in the direction of rotation, curl your fingers around in the direction of rotation, and then your thumb is going to stick up in the direction of angular velocity. For right now, we're talking about energy. It doesn't matter because times omega hat, which is use right hand to get that. For now, it doesn't matter because we're interested in, in energy, which doesn't have a direction. So let's calculate some moments of inertia just to make this concrete. Okay, so let's say we have, let's go back to our spheres and rods here for a minute. So let's say here's 4 kilograms and 4 kilograms and 4 kilograms, and this is 3 meters long. Now it's fairly clear the center of mass of this thing is going to be in the center, but what is this moment of inertia? Well, so it's going to be 4 kilograms times 3 meters squared. That's for object 1. And it's going to be another 4 kilograms times 3 meters squared for object 2. And it's going to be another 4 kilograms times 3 meters squared for object 3. And so that gives us, what does that come out to? 4 times 108. And the units must be kilogram meters squared, yes? Okay, now let's suppose that instead of that, we had 6 of these balls, and they each had masses of 2 kilograms. And that's still 3 meters what would the moment of inertia be here? Will it be 2 kilograms times 3 meters squared times 6, which would give us exactly the same moment of inertia. It would give us 108 kilogram meters squared, right? Okay. What if we had a solid hoop of uniform density with a radius of 3 meters and a mass of 12 kilograms? What would the moment of inertia of this thing be? Well, if we broke these, yep, you're exactly right. It's going to be 108 kilogram meters squared. It's just like taking these balls and breaking them up into smaller and smaller pieces and gluing them together to make a hoop. So you still get the same moment of inertia. Okay, so let's see if we can put this together. So we have the definition of moment of inertia is the sum of m1 r1 squared plus m2 r2 squared, where we're talking about the perpendicular distance. The rotational kinetic energy of something is a half times the moment of inertia times the angular speed squared. So let's see if we can actually figure out the rotational kinetic energy of something here. Okay, let me make that just a little smaller so that we can get our equations on the screen at the same time. So here's a problem to work on for a second. We have two balls. They have mass 0.7 kilograms. They're connected by a low mass rigid rod. The object is rotating clockwise, it looks like, around a pivot at its center. Its angular speed is 13 radians per second. What's the rotational kinetic energy of the object? Okay, let's see if we can do this. So this is going to take a minute. So see if you can do the calculation. Give you a couple minutes to do this. And Chris, yeah, so Chris is saying, how could you get the moment of inertia of a disk? And one way to think about calculating the moment of inertia of a disk is that suppose you conceptually divide it up into a series of concentric rings. It's easy to get the moment of inertia of one of the rings, so you could actually add those. But yes, basically what we do to get moments of inertia is by using calculus to divide solid objects up into lots of little pieces and then sum over all those pieces to get the moment of inertia. Well, this is really more like just a conventional integral, actually. Okay, so very good. You were actually able to take these equations and apply them to this problem and get an answer. So good job. 2 is correct. That is the rotational kinetic energy is indeed 4.73 joules. So good work. Just to go over it quickly, first we have its 2 steps. First we have to get the moment of inertia, right? Which is the mass times 0.2 meters squared times 2, because there are 2 of them. So this is, you had to realize that that was 0.2 meters. And so you got the moment of inertia, which was 0.056 kilogram meters squared. And then the rotational kinetic energy was a half I omega squared, which was 0.5 times what we got above, 5.6 kilogram. Okay, let's make that readable. 0.56 kilogram meters squared times the angular speed, which is given to us as 13 radians per second squared, and we got 4.73 joules. Okay, so well done. Good job. Yeah, Mitch, so what we're getting at here is indeed that now we have the ability, if we're interested in it, to resolve this energy relative to the center of mass, resolve kinetic energy into pieces, a piece associated with the translational motion of the center of mass of the object, and then pieces involved with motion relative to the center of mass of the object. And rotation is kind of a big one. So it's pretty useful to be able to get that. Now, the energy principle, of course, still applies here. So E final is still equal to E initial plus work done on a system. And so we can relate work to changes in, for example, rotational energy, right? So suppose we had some sort of a wheel here with, give it some spokes, and we have a string wrap around it. So, and then we exert a force. We pull up with some force F, and this is mounted on an axle. So what it does is it makes the wheel spin. So so we can use the energy principle to calculate things like if we pulled up for a while and the rate of rotation changed, how much work would we have done? So let's say initially, it's 3 revolutions per second, and its final speed is 7 revolutions per second. The mass of this thing is 3 kilograms, and its radius is 0.4 meters. How much work was done? So you pulled up, made it go faster. How much work did you do? Well, we've got, this thing is not, so it's not, the center of mass is stationary. So all we have here is this rotational kinetic energy. So if we write E final is E initial plus work, we have a half I omega final squared is equal to a half I omega initial squared plus however much work you did. So we need to actually figure out some quantities here. So we need to know the moment of inertia, and we need to know the initial and final angular speed, right? So the moment of inertia is just going to be, well, this is our hoop that we've been talking about where the mass is all the same distance away. So it's, the moment of inertia is just going to be 3 kilograms times 0.4 meters squared, which is going to give us 0.48 kilogram meters squared. Now we know, okay, so how do we get an angular speed out of being told how long it takes to go around? Well, we know that the angular speed is just radians per second, so it goes 2 pi radians in a third of a second. So that's 6 pi radians per second. And omega final is 2 pi radians in a seventh of a second. So that gives us 14 pi radians per second. And so the final kinetic energy is going to be a half times the moment of inertia, which is 0.48 kilogram meters squared, times 14 pi per second squared is a half times the moment of inertia times 6 pi per second squared plus work. And we can solve for the work. This gives us, now there is discussion in the textbook of how to calculate moment of inertia for various solid objects. And it does require calculus. And so basically the idea is that you divide some object like a rod up into pieces, and then each piece is the same mass, and you just sum over this, and you could get the moment of inertia. And if you make these pieces small enough, then you can actually just do an integral. We're not really very interested in actually doing that. It's just geometry and not really that much physics in it. So we give you the results for some standard geometry things. So for example, a rod, so a rod rotating around that axis, the moment of inertia is 1/12 times the mass times the length of the rod squared. For a disk, you do not need to know these things, okay? These are not things you want to memorize. Don't clutter up your brain with stuff like this. So the moment of a disk or a cylinder is a half mass r squared. Okay, so there's a sphere rotating around an axis through the center of the sphere is 2/5 mr squared. So that kind of, and you'll find a summary of these things in this is chapter 9. We're skipping chapter 8 for now. We're going to come back to it at the end of the semester so that some of the ideas in it are actually fresh when we need them. So this is stuff you can look up, okay? You don't need to memorize it. And notice that the moment of inertia of a rod rotating around its long axis would be completely different. So if it's rotating around its long axis, then the distance, all the atoms are really much closer. And so you get a totally different moment of inertia than you would if it's rotating around an axis perpendicular to the axis of the rod. Okay, what questions do you have? Yeah, if it's rotating on the long axis, it's basically a long disk, isn't it? Because remember that the distance we're taking is the perpendicular distance from the axis to the atom. So it's this. Moments for really odd shapes are always interesting and challenging, and you have to figure out how to divide your interesting really odd shape into some other shapes and sum over them. And if it's a really odd shape, you're just going to have to do it numerically. Okay? So you're actually just going to have to divide it into pieces and add it up numerically. There isn't going to be an integral that you can do to give you a nice thing. Okay, so here's my question for you for attendance, and it's actually the same question I asked last time, which is, in your opinion, what is the single most important idea that we discussed today? Okay, not a core dump of everything, but just the one thing that you, in your opinion, is the most important idea. Think about it and type your answer in chat. You may use private chat if you prefer. But I kind of like seeing everybody's answers in chat.